Hi. In today's video, we will talk about the limitations of deep learning. In particular, we will discuss adversarial attacks, data bias, and uncertainty. So here we go. As we've seen throughout the course, the historical perspective of AI is something very important. We only had to look back at the past, is what happened, so we can prevent it happen again in the future. And for AI, the AI hype and the AI winter is something that happened not only once but twice in the past. So you see this curve right here. AI existed for since the 50s, and it has suffered through a lot of up and down, and you can see this sort of a roller coaster. But there's periods of AI winter when expectation did not get fulfilled and the investment dwindle. So you don't want to have repeated this in the near future, even though we are enjoying the explosive growth currently. So let's talk about some of the possible limitation of AI currently that may get us into another AI winter, and potentially think about what are the potential solutions to overcome these challenges. First off, we have a very interesting algorithms by George Sibensky, who is a mathematician in 1989. And his theorems, and proven by him as well, is that a deep feed-forward neural network with a single hidden layers is sufficient to approximate to any arbitrary precision or accuracy any continuous function. So what does that mean? What he's saying is, given a neural network that is large enough with a single hidden layer, he can then predict any arbitrary continuous function to a very accurate results. A neural network with one hidden layer can do all this. Right? But they have a few caveats, of course. The number of hidden unit will be unfeasibly large, right? And the detail about how to train such a network still are not fully discussed, and this network might not be generalized, right? But through all this, it also show us one really interesting things, that if we have just a network, I believe what it does is just memorize all of the training example that you give into it. To give enough large enough training data, large enough network, all the network's doing is just memorizing the training data. And there is some modern demonstration of this rethink generalizations in neural net. And there's a paper by Yang and others in ICLR in 2017. And they do a very interesting experiment, right? So they have all of these images of different objects. And what they do to these label of these images is that they're going to throw a dice and then reshuffle the label. Now, keep in mind that they're not going to replay the text of the label here. But what happened is, given a label, they're going to shove a dice. So they're randomly going to replay that label with a randomly selected label. So a dog here can become a banana, and banana happen to become a dog. However, this dog then can become a tree, because this is the stochastic process, right? So you can see here now a dog, different sample of dog can become a different class. One become banana and one become a tree. So these classes are now from a same class become now a disjointed classes. And banana become a tree may become a dog, or other classes. So this whole randomly process, you would think would mess up entirely the training sets, and the algorithms would not be able to generalize very well. And you probably is right. As a result, they show that depend on the level of randomization, the performance of this neural net based on some test sets would reduce when the randomization increase, which make a lot of sense. But perhaps what even more interesting is this. For the training set, in all cases, regardless to the randomization of the label, the training data eventually will achieve very, very high accuracy, close to 100%. So what we've shown here is that all of these networks, given enough parameters, any modern neural network can perfectly fit to a random data. Do not mean it's perform well, but it would tell you that it do really well on the training data. Right? So sort of that a danger, with the universal approximation theorem, it can still approximate any continuous functions just fine, like George Sabensko said. But it does not mean it would have any usefulness in the test set or unforeseen data. Right, so that's sort of a danger that we're facing as well. We train a network on some training data without any implication to how it's gonna do in the testing data. We may as well memorizing the training data, right? And that's the danger. Okay, so another thing is really had to be clarified here is the recognition of neural network do not mean understanding. Right? For example, a model can generate caption for this image, accurately describe the pictures, right? But that doesn't mean that it understands the content of the picture or the caption it generates. Right? We might think that it is understanding the content of the image or understand the words that it generates. It doesn't understand either. And the reason why I said that is for any slight change in a training set, it might predict something completely out of place and observe caption, right? So for example here, it generates a caption saying that holding a baseball bat. Clearly, we all know the baseball bat, for human, it can't possibly be that small. Right, so these are dealing with not the understanding, but just rather the matching words into certain concept that it learns. So we had to separate these concepts. Even though neural network was able to classify thousands of classes, it doesn't really understand the classes. And even though the neural network will successfully beat the best Go player in the world, do not mean understand fully the joy of playing Go, right? What it means to play Go, right? It's just purely figured out the best way of the next step, but it doesn't understand the purpose of playing Go, right? So in that regard, we still have a bit of a gap in the understanding of how neural networks operate or how it perceive a certain concept. Okay. So we're gonna visit a certain limitation here. We already have some limitation about neural network that kind of explained throughout the course. For example, it's very data hungry, it requires a lot of training data. It's computationally expensive to train and deploy. Most of the time, people view it as a black box, which is not explainable and pretty difficult to trust. And also is very finicky to optimize, take a lot of fine-tuning, setting of hyperparameters, choice of the architecture, and so on. But today we're going to add a few more items to this list. We're going to talk about how the neural network can be easily fooled by adversarial example. It can be subject to algorithmic or data bias, and also it is poorly structured to represent uncertainty and difficult to encode structure of a prior knowledge. So we're going to talk about each of these three items, right? First is adversarial attacks, and you may have heard about this on the news or some recent paper. So the scenario is that you have an image and it was perfectly classified by a neural network. Say, example, this image is a sport car. And then you would add some noise into this image called adversarial noise. So you look like all random noise here, and you add it to the image, so you just additive to the pixel. And then certainly the neural net cannot correctly classify this anymore. And to our eye, that's still basically example a sport car and no mistake about it, right? So these two images for us should both have the same label. But for a neural net, now I think it's a toaster. What a bummer, right? So what really happened here is that this attack noise is not random at all. It's actually learned signal to fool the network. Okay, so let me explain. So we train our neural network using gradient descent, and for the most part, this is the formulation of it, right? You trying to update the network parameter based on some learning rate that go on the opposite direction of the gradient of the network, right? So this gradient, basically what you're trying to do is fix x and y and then change w, right, so with respect to w, so that our loss would decrease over time, right? In fact, you put a minus sign here so that we go opposite direction of the gradient and therefore that descends or reduce the loss. So we all know that so far. So using a very similar formulation in adversarial attacks, the attacking image would modify to increase the errors. So what we do here is fix the network parameters. This is maybe some model that was given to you. So the W was fixed in this case. The Y is fixed as well, the label of the image. What changed now is the image itself. X will be changed. So X, the way it will be changed is that it will be added with some learning rate, the gradient with respect to X. What does that mean, right? So what happened here, we fixed W and Y. We want to change X so that our error would increase the most. And the reason we increase is right here. Like our purpose is trying to fool the network, which means we want to find the kind of example that increase the errors the most, right? So how does a small change in X here increase the loss, right? So you see the sign changes here as well. And so by iterating over this, the X will be changed so that the error increase the most. And so the image that you see, the sport car image that you see with some modification in there would fool the network because it's increased the loss of the network the most. And given any W and Y, you can actually train this adversarial example. So here's more adversarial examples that was able to fool the network. The signs, traffic sign, with adversarial example, it now think it is a stop sign. It changed the speed limit from 120 to 30. It changed the logo of some company before become a stop sign or not overtaking sign. The custom sign attacks seem like an empty sign now. It's so say speed limit 30, but it's actually just some random, look like random harmless noise, and so on and so forth. And also, some what happened is the lenticular view. So when you change the sign angle or something, you will get a different classes. So just saying that the networks are vulnerable for these kind of adversarial attacks, and thus may have some security concern when you deploy this kind of neural network in the real world. Okay. Next, we go into issues of data or algorithmic bias. Right? So we are familiar with the ImageNet, and over the year, more and more neural net were able to perform better in the ImageNet performance. And until this writing or presentation, the state of the art have achieved a top 5 errors on the ImageNet of 1.3%. So the error is now 0.3%. For many ImageNets consider a solved problem. So the convolutional neural net had become very, very well designed. And people start looking to other data set that is more challenging, and perhaps with open images data set, there is a wide community around the world who contribute to this data set. So the open image data set now have over 9 million images and over 6,000 labels. And remember, ImageNet also only have 1,000 examples, so you have 6,000 label here, which is quite a lot more. And the reason they can get this is because they also have multi-label instead of one label like in ImageNet. So there is a GitHub page for the open image. If you want to check it out, you can download and play with it. And this all has some very interesting difficult classes that you can see. I show an example here of a staircase, image of a staircase, and you can see how difficult that may be for a machine learning algorithm to classify them as staircase and not something else, right? Very interesting directions and shapes and sizes. Okay, so for an algorithm to train on these classifications, on this open image, given, for example, this image, it may be able to obtain some label, such the top 5 classes that it obtain would be this: bride, dress, ceremony, woman, and wedding. And you say, well, that's spot on, right? That's exactly what the image contained. The top 5 classes, perfectly right. And that's fine. The trouble come when the algorithm was shown with this image. And this image is a Indian bride at her wedding, and there is a ceremony in her wedding. So this image, if given to a classification model trained on open images, guess what is the top 5 classes that it predict? Top 5 classes are clothing, event, custom, red, and performance art. So there is nowhere weddings found. There's nowhere a ceremony. There's nowhere the bride was mentioned. And even worse, there's nowhere a woman was on the top 5 classes. And so there is some concern over this, because obviously the algorithm didn't understand the cultural significance of this image and confuse it with something else completely, right? So there is effort dig into what happened, and this is what they see. They look at the geographical contribution of the training data, and you can clearly see here in this graph that most of the training data come from North America and Europe, and little from anywhere else. So there is certainly a geographical bias in the training process of these images, and thus those bias creates any sort of problem when the algorithms are put into tests, maybe worldwide, right? So the bias in data in algorithmic is also a statistical co-founder from the societal bias. The lesson to take away here is to beware the difference between the training set and the inference set or testing sets distribution of the data. You cannot train it on a certain geographical location or include any sort of bias and then try to deploy it in a broader region geographically or other data set that may not be representative. And so, also don't take any data set without first questioning it. And the third limitation of machine learning here, I can tell you, is about uncertainty estimation. So far, we train our method, and you may have some neural network like this to classify dogs and cats, right? So your training data come in with cats and dogs, and it was able to inference the probability distribution of whether that subject being a dog and a cat. However, this probability distribution have nothing to do with the uncertainty or the confidence of the network about this object. It's simply just a softmax or a fit distribution over all of the classes. So there's a difference between that uncertainty distribution and the uncertainty or the confidence of the network when predicting these classes. And the example for this is that if I feed in an image of something it haven't seen before in the training, maybe an image of a horse, it will still confidently said, in this case, very confidently, that's image of a dog. And, they have 20% of a cat. Because it had to be added into one, right? But it didn't say, I'm not sure. It didn't say, I'm not sure about this image of something I haven't seen. So there is no notion of uncertainty or the confidence of the network based on some unforeseen prediction, right? So we're going to need a uncertainty metric to assess how the network confidence in its prediction, right? And that gives rise to a very emerging field called Bayesian deep learning for uncertainty. And the way it works is regularly network trying to predict the output directly from raw data, and using a mapping functions, right, the nonlinear and linear mapping function, and parameterized by some weight. And our formulation was trying to minimize loss. Okay. Now with Bayesian deep learning, the goal is trying to learn a posterior distribution over the network's weight, and that posterior distributions are given by Bayes' rule, just like here. The problem with this is estimate this quantity directly is untractable, right? So if you given x and y, it's very difficult to infer the posterior distribution of the network's parameter abuse here. So there's some effort have been done on the field trying to approximate this posterior distribution using sampling. Right, so we're gonna try to see how confident the network is, or this probability using sampling technique. Right, so stochastic sampling for uncertainty. Okay, so what we're gonna do is that we will evaluate T forward passes to the network, and each of the time learning a different parameter weight. Right. And you can think about this as some sort of dropout. So you learned about dropout earlier. You can think about this as some sort of dropout by fitting a Bernoulli distributions over the weight. Right? Don't be a Bernoulli mean here is that you can think about it is that you fit a distribution so that you can stochastically determine whether each of the parameters is used or not. So very similar to a concept of dropout, right? So in a convolutional neural net, what it means here is that if you have some unregularized kernels here and you fit a Bernoulli dropout distribution, what happens is some of these network weight will be completely blocked out or set to be empty or non-determination, so that it won't be affect in the calculations of the predictions and inference. So for example, if you fit the Bernoulli dropout here, now you have a stochastically sample addition of the network's weight. And what you're going to do next is that you're going to use that portion of the network and try to inference the label, right? And then you can do that T times, each of them time having slightly different settings of the network. And at the result, now you have T different network, and it may be predicting different things. And what you can do then is that you can calculate the uncertainty by approximating the expected value of the means of these calculated value, and also the standard deviation or the variance. So using this, you now have a better idea about how uncertain the networks toward a task. Right? So hopefully that gives you some notion of uncertainty of the neuron, or its confident certain toward its prediction. And that's just a sort of a start on this direction, and hopefully we'll be able to learn more and explore in terms of the research community about this uncertainty. And an application that you can see here is maybe given an input image, and you have to approximate the depth of this image, the depth, right? So this is a predicted depth. So like, okay, looks pretty good. But what even more importantly, where is the uncertainty of the model? Like where the model is not sure about its prediction, right? And this is an image showing the heat map of the model uncertainty, right? And you can see red here is less uncertain about, well, actually more uncertain about the prediction. So you can see the area around the red car here. And that kind of makes sense, right? So what you look at this flat image, and the reason among the two cars, especially the one that have glasses that may reflect light from other surface, it would be fairly difficult to approximate the depth. So you can see there's mirrors areas here, and the area around the car will be more difficult, thus higher uncertainty to predict. Right, so you at least have some more notion about how confident the network is toward its prediction. Okay, so in summary, we discussed a few more this limitation of deep learning, and this certainly give room for our further research, our further study, investigation in deep learning, try to improve it. And there's certainly things that we can improve in deep learning. Currently, deep learning is easily fooled by adversarial example. It can be subject to data or algorithmic bias, and it is still poorly structured at representing uncertainty, and it's difficult to encode the structure with any prior knowledge. So hopefully that gives you some notions of what you can do to improve deep learning in the future, and how to avoid from the situation where your deep learning system is limited by these limitations. All right. That closes our discussion on limitation of deep learning. We will discuss more on the explainable AI on the next video. So I'll see you then.